Parts of pom.xml. Maven dependencies are typically archives such as jar, var, enterprise archive like EAR, and zip. Each Maven dependency is uniquely identified using the following group artifact and Maven coordinates, version coordinates. Group ID. Group ID is identifier of the organization or group that is responsible for this project. For example, org.hibernate log4j, or for Spring Framework, it is org.springframework.boot. The next coordinate is artifact ID. Artifact ID is the identifier of the artifact being generated by the project. This must be unique among projects using the same group ID. For example, Hibernate has Hibernate tools, and Spring has Spring Core, Spring Data, Spring Batch, and so on. The version coordinate. Version coordinate indicates the version number of the project. For example, 1.0, 2.3.1 snapshot, or 436.final for say a Hibernate project. Type coordinate. Type coordinate indicates the type of packaging of the generated artifacts such as jar, var, and ER, or a POM. And we'll read more about this in later videos. Scope coordinate. A POM project or a Maven project can have many different kind of scopes. The first is compile. This is the default scope. Any dependencies defined under the compile scope will be available in all the class paths. It will be packaged into the final artifact produced by the Maven project. If you are building a var type artifact, then the referred jar file with the compile scope will be embedded in the var file itself. The other is the provided. Provided scope would expect that the corresponding dependency would be provided by the JDK or a container that runs the application. The best example is the Servlet API. Any dependency with the provided scope will be available in the build time class path, but it won't be packaged into the final artifact if it's a var file. The Servlet API will typically be available in the class path during the build time, but won't get packaged into the var file. These are typically provided by, say, server like a JBoss or Tomcat. Runtime scope. Dependencies for runtime scope are defined, and the runtime scope will be available only during the runtime, but not in the build time class path. Dependencies defined on the runtime scope will be available only during the runtime, not in the build time class path. The dependencies will be packaged into the final artifact. You may have a web-based app that talks to a MySQL database in runtime. Your code does not have any hard dependencies to MySQL database server. This code is written against the Java JDBC API, and it does not need MySQL database driver at a build time. However, during the runtime, it needs the driver to talk to the MySQL database, and for this, the driver should be packaged into the final artifact. The next scope is test scope. In test scope, dependencies are only needed for test compilation, for example, JUnit or TestNG or Mockito, and execution must be defined under the test scope. These dependencies also don't get packaged into the final artifact. System scope. This is very similar to the scope provided. The only difference is that with the system scope, you need to tell Maven how to find it. System dependencies are useful when you do not have a referred dependency in a Maven repository. With this, you need to make sure that all the system dependencies are available to download with the source code itself. It is always recommended to avoid using system dependencies. Import scope. This is only applicable for dependencies defined under the dependency management section with the packaging type POM. Transitive dependency. Dependency declared in your project's pom.xml file often have their own dependency. Such dependencies are called transitive dependency. Take the example of Hibernate core. For Hibernate core to function properly, it requires JBoss logging, DOM4j, Java assist, and so on and so forth. The Hibernate core declared in a pom.xml file is considered a direct dependency, and dependencies such as DOM4j and Java assist are considered your project's transitive dependency. A key benefit of Maven is that it automatically deals with transitive dependency and includes them in your project. To do this, Maven uses a technique called dependency mediation to resolve version conflicts. Simply stated, dependency mediation allows Maven to pull the dependency that is closest to the project in the tree as shown in the figure. In this figure, there are two versions of dependency B, 0.0.8 and 1.0.0. In this scenario, the version 0.0.8 of dependency B is included in the project because it is a direct dependency and is closest to the tree. Now look at the three versions of dependency F. They are 0.1.3, 1.0.0 and 2.2.0. All three dependencies are at the same depth. Now in this scenario, Maven will use the first found dependency, and which would be 0.1.3 and not the latest 2.2.0 version. Now one point that needs to be noted here is that although highly useful, transitive dependency can cause problem and unpredictable side effects, as you might end up including unwanted jar file or older version of jar file. So always analyze your dependency tree and make sure you are bundling the dependency you need and excluding the ones you don't require. And to find that out, you can run the same command that we used earlier, that is maven help effective pom. Dependency exclusion. To avoid the issue of transitive dependency where Maven may pull unwanted or older version of transitive dependency of Maven, Maven provides a feature called dependency exclusion. Dependency exclusion helps to avoid getting a selected set of transitive dependency. Say for example, in our project 3-1, JUnit already comes with a Hamcrest core, but it might be an older version and we may need to use Hamcrest library jar file, which also pulls in Hamcrest core, a newer version, and thus there will be conflict, so we excluded the Hamcrest from JUnit dependency. So that brings you to the end of this lecture. See you in the next lecture.